I mean, imagine you are a marine biologist, right? It's the year 1901.
Okay, setting the scene.
Yeah, you're diving off the coast of this remote Greek island, exploring a shipwreck from like 2,000 years ago.
Right.
You pull up statues, pottery, uh, normal historical stuff, and then encrusted in this big lump of corroded bronze, you find what is essentially a fully functioning analog smartwatch.
Just buried in the mud.
Exactly, mechanical computer just chilling alongside guys in togas. I mean, we have this pervasive tendency to view human progress like an escalator, you know?
Oh, absolutely, the escalator myth.
Right, like we are standing at the very top, looking down at the past, assuming that every step forward just naturally, inevitably builds on the one before it.
Because we have supercomputers in our pockets now.
Exactly. So obviously we must be at the absolute peak of human technological achievement.
It's a very comforting narrative, honestly. Viewing history as a continuous upward slope gives us this sense of guaranteed momentum.
Yeah.
It implies that humanity never really slides backward.
But then you stumble across a stack of sources like the ones we're deep diving into today, and suddenly that historical escalator completely jams.
It really does.
The gears grind, and you realize it might actually be moving in reverse. Welcome to today's deep dive, everyone. We are looking at this fascinating breakdown of ancient technologies that modern science, with all of our electron microscopes, our AI modeling, our massive research budgets, still cannot fully explain, let alone replicate.
And these aren't just quirky historical footnotes.
No, not at all.
We are talking about physical artifacts and engineering marvels that totally defy the timeline of human invention. They are physical proof that knowledge doesn't just march forward.
Right.
Sometimes profound, world-altering scientific understanding is achieved, utilized for centuries, and then completely erased from existence.
It's wild, and the sheer scope of the source material today is huge. I mean, it touches on Greek fire, which is this unextinguishable liquid flame the Byzantine Empire used to incinerate enemy fleets.
A chemical weapon so secret they literally took the recipe to their graves.
Literally. It also breaks down the massive 130-ton mortarless stones of Sacsayhuaman in Peru that fit together like a microscopic 3D puzzle. And the Voynich manuscript, this book, written in a language that even modern decryption algorithms cannot crack.
It is a massive catalog of lost human ingenuity.
It really is. And, you know, to protect you from total information overload today, we're going to leave the uncrackable codes and the giant rocks for another day.
Good call. Keep it focused.
Yeah, we're zooming in on just 3 specific inventions from this stack. 3 technologies that frankly feel like glitches in the matrix. Because when I first read this, my immediate reaction was just deep skepticism.
Which is fair.
Right? I thought, are we really saying ancient people were outperforming modern material science? Or are we just romanticizing the past because we lost the blueprints?
Well, skepticism is the healthiest starting point, I think. The burden of proof should always be on the extraordinary claim.
Exactly.
But the physical evidence in these 3 specific cases forces modern researchers into a very uncomfortable corner.
How so?
Because the artifacts are sitting right there on the lab tables, we can test them, and modern science is legitimately struggling to catch up to what our ancestors were doing millennia ago.
Okay, well, let's jump into the first glitch. Because it's one thing to lose the recipe for a chemical weapon, but losing the concept of complex computation.
Yeah, that's a big one.
We assume computers are a product of the 20th century. You know, Alan Turing, IBM, silicon chips. But that 1901 shipwreck you mentioned completely shatters that timeline.
It does. That wreck was found off the coast of the Greek island of Antikythera. The ship went down around 65 BC.
65 BC, just let that sink in.
Right, and when those sponge divers brought up that corroded lump of bronze, nobody thought twice about it. It looked like a crusty sea rock.
Criska rock.
It sat in a museum, ignored for months, until the corrosion naturally split open, and an archaeologist noticed tiny, precision-cut bronze gears inside.
Wow.
Dozens of them interlocking inside a device that predates the Roman Empire's peak.
And we call it the Antikythera mechanism now, right? The source notes, it contained at least 30 surviving bronze gears, originally housed in a wooden box about the size of a shoebox.
A very small package for what it did.
Yeah, it had dials on the front and back, and it was computing astronomical data. It predicted solar and lunar eclipses, tracked the 5 visible planets, and calculated the timing of the Olympic Games.
Which is astonishing on its face, but the mechanical reality of how it achieved this is what keeps engineers up at night.
Okay, but here is where my initial skepticism flared up hard.
Yeah.
Calling this thing an analog computer feels like a massive modern stretch.
Oh, I hear that a lot.
Right, Because a grandfather clock has gears.
Right.
A Muget box has gears. Wasn't this just a highly complicated, clarified clock?
That is the natural assumption, yeah.
Uh,
But a clock measures a constant, steady progression of time. One gear turns another at a fixed, unchanging rate.
okay.
The Antikythera mechanism was performing mathematical operations. Think about how gears work. If you have a gear with 10 teeth turning a gear with 50 teeth, you are physically performing division. You are changing the ratio of movement.
Oh, wait. So it's like a physical spreadsheet.
Yes.
Like if I change the value in one cell of a spreadsheet, the formula automatically updates all the other cells.
Exactly.
So if I turn the crank on the side of this box to input a date, the gear ratios are acting as physical math formulas, spinning all the other dials to output the exact positions of the cosmos on that specific day.
That is a brilliant way to frame it. It is literally a physical spreadsheet made of bronze, but it goes even deeper than basic division.
Seriously?
Yeah, the most staggering feature of the Antikythera mechanism is how it tracked the moon. Because the moon doesn't move through the sky at a constant speed.
Oh, right, because its orbit is elliptical.
Exactly. It appears to speed up and slow down depending on where it is in the sky.
Right, and capturing that requires some pretty advanced math.
It requires calculating anomalies. To replicate that irregular speeding up and slowing down motion using perfectly circular gears, the Greek engineers used something called epicyclic gearing.
Epicyclic. What does that mean mechanically?
They basically mounted one gear slightly off-center on the face of another gear,
Okay.
and they connected them with this tiny pin and slot mechanism. So as the bottom gear turned at a constant rate, the pin sliding in the slot caused the top gear to accelerate and decelerate,
Wow.
perfectly mimicking the moon's actual orbit.
They were doing calculus with metal.
They were translating high-level, complex astronomical geometry into microscopic mechanical engineering. And to understand why this shouldn't exist, you just have to look at the timeline.
Right, because when did we see this again?
After this device was built, humanity would not create a gear system even remotely this complex for another 1,400 years.
That's crazy.
Not until the astronomical clocks of the European Renaissance.
Over a millennium of mechanical darkness. And we've scanned this thing, right? Like, the transcript mentions modern X-rays, CT scans, 3D modeling.
Oh, yeah, over a century of intense study. We know the gear paths, we know what it was calculating, but fully replicating the ambition, the microscopic precision of the hand-filed teeth, and the sheer genius of cramming all that mathematical power into a shoebox-sized device, that is something modern engineers still marvel at.
But you know what? The detail that absolutely broke my brain wasn't the gears themselves. It was the location.
Oh, the cargo ship.
Yes. I just realized as I was reading the source, this wasn't found locked away in some heavily guarded temple. That wasn't the prized possession of an emperor. It was found on a cargo ship.
Just surrounded by jugs of wine and bulk statues.
Exactly. It was commercial freight. I mean, think about the implications of that.
Right.
If you're casually shipping a 30-gear analog computer across the Mediterranean on a standard cargo run, this wasn't some one-off anomaly built by a lone genius in a case.
No, it implies an entire lost industrial ecosystem. You don't have one of these on a cargo ship unless you have workshops producing them, which means you had a supply chain mining and refining the bronze to the right tolerances. You had an educational system teaching the complex trigonometry required to design the gear ratios.
Yeah.
You had specialized tools for micromachining. An entire industry of advanced micromechanics was completely erased from the historical record.
Which raises an incredibly unsettling question. Because it's one thing to lose the blueprint for a shoebox-sized computer. A workshop burns down, a few master craftsmen die, and the secret is gone.
Sure.
But how do you lose the recipe for the building blocks of an entire empire? That brings us to our second technological glitch. Roman concrete. We are zooming out from the micro to the massive here.
The jump from micromechanics to macro infrastructure really highlights the breadth of this lost knowledge.
Totally. Let's talk about the Pantheon in Rome. It was finished around 125 AD, and it boasts a 142-foot wide dome.
Which is still massive by today's standards.
Right. It is the largest unreinforced concrete dome in the entire world. Even today, no steel bars holding it together, and it has been standing for nearly 2,000 years, surviving earthquakes, barbarian sacks, floods, you name it.
Contrast that with modern Portland cement, the stuff we use to build our highways, our skyscrapers, our parking garages.
Yeah, how does ours hold up?
Well, modern concrete is incredibly strong under compression, but it's very brittle. We have to reinforce it with steel rebar. And even then, it generally starts cracking and degrading after about 50 to 100 years.
We spend billions annually just patching crumbling bridges. Our modern mix simply cannot touch what the Romans were mixing by hand in wooden troughs 2 millennia ago.
It's pretty humbling.
It is. But again, my skeptical brain kicked in here. I immediately thought about survivorship bias.
Ah, the classic counter-argument.
Right. Like, we're only looking at the Pantheon because it's the one building massive enough to survive. They built the walls 20 feet thick. Of course it survived. What about the thousands of regular Roman buildings that crumbled to dust?
Survivorship bias is a very real trap in history, absolutely. But the longevity of Roman structures isn't just about thickness.
Okay, so what is it?
In 2023, scientists at MIT cracked a massive piece of this mystery, proving that the material itself is chemically superior to ours.
Wait, chemically superior?
Yes. They analyzed samples of Roman concrete and focused on these tiny, millimeter-scale white chunks embedded in the matrix. They're known as limeclasts.
And for decades, structural engineers thought those white chunks were just evidence of sloppy Roman mixing, right? They figured the builders just didn't sift their volcanic ash and lime well enough.
Exactly. They dismissed them as primitive imperfections.
But they weren't.
Not at all. The MIT team discovered those chunks are actually a highly intentional active ingredient. They are the engine of the concrete's longevity.
Okay, how does that work?
Well, think about when modern concrete cracks, which it always does from settling or thermal expansion.
Right, you always see cracks in sidewalks.
Water seeps into the crack, it reaches the steel rebar, rusts it, and the rust expands, blowing the concrete apart from the inside.
But what happens when a crack forms in Roman concrete?
When water seeps into a crack in Roman concrete, it hits those tiny white limeclasts. The water causes the calcium inside the clast to dissolve, creating this highly reactive, calcium-rich solution.
Okay.
That solution then naturally reacts with the surrounding materials and recrystallizes as calcium carbonate.
Wait, it essentially grows new rock inside the fissure.
It automatically fills and seals the crack before it can spread.
The building has an immune system.
Yes.
That is exactly what a human body does. You get a cut, blood rushes to the area, it coagulates, forms a scab, and heals the breach. The Romans built structures that literally scab over and heal their own wounds.
It's brilliant.
And the most ironic part of the source material is what triggers this healing.
Water. Specifically, in many of their coastal structures, seawater.
Seawater,
Yeah.
which is the absolute bane of modern infrastructure.
Yeah.
It violently eats away at our structures. But for the Romans, splashing seawater against their harbor walls actually activates this chemical reaction, constantly fortifying the concrete.
It's incredible, and modern engineers are furiously trying to reverse engineer this. Imagine self-healing roads or seawalls that never need maintenance.
That would change everything, so why aren't we doing it?
Scaling it up is the hurdle. The Romans relied on a very specific volcanic ash called pozzolana mined from the Bay of Naples region.
Well, so it's a local ingredient.
Right, it has a unique chemical signature. Trying to replicate that exact reactive environment synthetically, cleanly, and at a modern commercial scale is proving incredibly difficult.
So we can stare at the Pantheon all we want, but we can't just go out and pour a new one tomorrow. It's wild. We lost the macro engineering of an empire.
You did.
But the final source we are looking at takes us in the exact opposite direction. Past the giant concrete domes, past the microscopic gears, all the way down to the molecular level.
Yes. For this, we are traveling to the early Middle Ages, to the workshops of the Middle East. We are talking about Damascus steel.
The legends around these swords are like something out of a fantasy novel. I mean, European crusaders wrote terrified accounts of Middle Eastern swordsmiths producing blades that could cut through heavy European broadswords like they were made of tin.
The sharpness was legendary. The classic historical test was dropping a silk scarf into the air and letting it float down onto the upturned blade.
And what happened?
The sheer weight of the falling silk was enough to slice the fabric perfectly in two.
That is insane. And you could identify a true Damascus blade by its look, right? The surface of the steel had these incredible distinctive swirling patterns resembling flowing water or rippling sand.
Right, and it wasn't decorative paint or etching. Those patterns were the physical manifestation of the metal's internal structure.
Which brings us to a massive scientific revelation. In 2006, researchers at a German university managed to acquire fragments of a genuine historical Damascus steel blade forged in the 17th century.
A rare find.
Very. They took these fragments and put them under a high-powered electron microscope to see what was actually going on inside that rippling metal.
And they found carbon nanotubes. Let that sink in.
For anyone outside of material science, what is that?
Well, a carbon nanotube is exactly what it sounds like. It is a microscopic cylinder formed entirely of carbon atoms linked together in a hexagonal lattice.
Okay.
They are incredibly small, but their molecular bonds make them one of the strongest, stiffest materials known to science.
This is the part where the timeline escalator doesn't just jam, it completely shatters.
Oh, yeah.
We, modern spacefaring humanity, only officially discovered carbon nanotubes in 1991. We use them today in cutting-edge aerospace engineering and nanotechnology. And you were telling me a guy in a 12th century blacksmith shop was intentionally manipulating carbon at the molecular level.
Let's apply some careful nuance here. Did a medieval swordsmith understand the atomic structure of a carbon lattice? No.
Right.
He didn't have a microscope. But the presence of those nanotubes wasn't a fluke. It was the result of an incredibly complex, highly refined process of trial and error.
So how did they do it without knowing what they were doing?
They used a specific type of steel called wootz, which was imported from India. It naturally contained trace impurities like vanadium and tungsten.
Okay, so the ingredients matter.
Deeply. When they forged this steel, they subjected it to very specific repeated cycles of heating and cooling. Under the electron microscope, scientists found that those impurities caused the carbon in the steel to form into microscopic, wire-like tubes, the nanotubes.
Okay, I think I get it. It's like baking a wildly complicated cake.
Go on.
Like, you don't need a PhD in microbiology to bake bread. You don't need to know that yeast is a single-celled fungus undergoing anaerobic respiration.
Right.
You just know that if you mix this specific flour with this specific starter and let it rest in a warm room for exactly 2 hours, the bread rises perfectly.
That is a perfect analogy. The blacksmiths were master chefs of metallurgy. Through generations of observable trial and error, they literally simulated cutting-edge nanotechnology.
And what do those molecular tubes actually do for the sword? Why does it slice silk?
The nanotubes encase incredibly hard crystals of cementite. Basically, you get microscopic hard wires embedded in a flexible steel matrix.
Oh, I see.
This gives the blade immense flexibility so it doesn't shatter in battle. But at the very edge of the blade, those hard nanotubes act like a microserrated saw at the molecular level.
Wow.
That is what gives it the terrifying, enduring sharpness.
But just like the Antikythera gears and the Roman concrete, this recipe was lost. The transcript notes that by around 1750, true Damascus steel stopped being produced.
Yeah, historians and metallurgists believe the specific wootz ores in India were eventually mined out or trade routes collapsed.
So they ran out of the magic ingredients.
Exactly. And because the blacksmiths only knew the recipe through observation, not through underlying molecular chemistry, they couldn't adapt. When they tried to use different steel ores with their traditional heating cycles, the nanotubes just didn't form. The magic was gone.
We have electron microscopes today. We can see the carbon cylinders inside the historical fragments, but we still cannot fully reproduce the accident on purpose to match the performance of the historical originals.
No, we can't. We can land a robotic rover on Mars using advanced orbital mechanics, but recreating the perfect, flexible, razor-sharp molecular lattice of a medieval sword still eludes our modern foundries. It really puts our technological ego in check.
It really does. So what does this all mean for us? I mean, we took a journey through 3 distinct scientific disciplines today.
Yeah. Quite the spread.
We have a Greek analog computer that modeled the eccentric orbit of the moon using physical calculus, predating similar mechanics by 1,400 years. We have Roman concrete that utilizes a chemical immune system to self-heal its own cracks, laughing at our crumbling modern highways.
Right.
And we have medieval swords laced with carbon nanotubes, nanotechnology achieved 8 centuries before we even discovered the molecule.
The overarching lesson here, I think, is a warning about the fragility of knowledge.
Yeah, absolutely.
We assume that because we have cloud servers and digitized data, our progress is permanently secured. But these artifacts prove that deep, profound scientific mastery can be achieved, perfected, and then utterly lost to the sands of time.
It's sobering.
A shift in a trade route, the fall of a political empire, or a sinking ship in the Mediterranean can literally erase centuries of innovation.
It proves that the modern scientific method isn't the only pathway to technological perfection,
Yeah.
The Romans and the medieval smiths achieved mastery through observation, trial, and generations of localized knowledge.
Definitely.
The fact that we struggle to reverse engineer their work today doesn't make their methods primitive. It makes them profound.
And it forces us to ask, if we lost the secrets to self-healing infrastructure and analog computation in the past, what vital knowledge from our own era might be vulnerable to being lost in the future?
That is a heavy thought. But I want to leave you with one final, slightly different thought to mull over today, bringing us right back to our starting point.
Yeah.
Remember the Antikythera mechanism? For months, it sat on a shelf in a museum. Everyone who walked past it thought it was just a useless, corroded rock recovered from a shipwreck.
Right, just a rock.
It wasn't until the bronze literally cracked open and someone with a curious eye bothered to look closely that humanity realized it was an impossibly advanced machine. So, here's the question. How many other rocks are sitting in museum basements all over the world right now?
Oh, that's a good question.
Just waiting for a curious observer, or maybe a brand new piece of modern scanning technology to realize that they aren't rocks at all, but the forgotten blueprints of a world we only thought we understood.
The ultimate puzzle.
Keep questioning the escalator, everyone. Thanks for joining us on this deep dive.